So let's say that in this logistic regression, as I said earlier, when you have a situation in which that your y variable is categorical. Okay, that categorical situation we haven't tackled that one. Can you remember that when you go to this classification of all the variables, at the end of the day, you have pretty much done all the procedures related to all these categories. Okay, this is what I'm talking about. See, okay, let's say that you have a x variable. X means independent variable. See, independent variable. See, independent variable. It might gonna be either quantitative, numerical, or categorical. See. Then on the other hand, y variable, dependent variable may be either quantitative or categorical. See? So when you have a situation like this, pretty much so far, we have tackled this one using different procedures. Look at the quantitative to quantitative. What do you use? You use regression. Can you remember? Regular regression. You have a x variable, independent variable, categorical, but a quantitative variable, the y variable is quantitative. Then what are you going to use? You're going to use analysis of variance, ANOVA. Can you remember? When you have a quantitative, x variable is quantitative or categorical, okay? Then quantitative to categorical, what do you use? Then you are using the logistic regression. See? Logistic regression. Or cat to cat, categorical to categorical, you can use what? Contingency table. Can you remember? Mainly contingency table plus, see, contingency table with chi-square test or logistic regression. I would say Ella logistic regression. So we are here. See, we have done this one. We have done that one. We even in this class or in the previous classes, we have already done those. So in logistic regression, your categorical, your y variable, the dependent variable is, it's in the classes, it's with the groups. Okay. In such a situation, how could you gonna tackle such thing? That's the kind of a discussion we are trying to build up over here. See, it has many aspects involved with that one. Let's try to build up piece by piece, and then at the same time we go through the example and then try to build up some knowledge on that one. You have already seen that one. As I said earlier, there are two aspects over here, contingency table versus the logistic regression, that formula. We're not going to go to the contingency table approach in this class. We don't need to, because you already built up that knowledge. That's the same thing being with the like a very formal and concrete and very robust procedure called the logistic regression being utilized for the same scenario that we're going to tackle with the contingency table. Sometime little bit I might gonna show you with the contingency table what it looks like. See, let's say that before we gonna get into that one, I would like to bring up some kind of like a research study that what we are trying to do over here. Let's look at some examples that describe. Okay, this one little bit, and then get the idea what we are planning to do over here. Look at I'm gonna make this one. See, look at this one. So our research study involved with that intervention designed to improve the health study of adults who have been diagnosed with prediabetes. Individuals with the prediabetes have elevated blood glucose of sugar, but this glucose level is not high enough to receive a diagnosis of a full-blown type 2 diabetes. Okay. of individuals with the pre-diabetes develop type 2 diabetes. From the pre-diabetes to the type 2, that development has to be stopped. That's what we are trying to do in this research, which can have serious health consequences. So in the attempt to stop the progression from pre-diabetes to full-blown type 2 diabetes, we suppose the researchers have identified 200 adults who have been diagnosed with the pre-diabetes. So now for this research, they have reached to the people who have already been identified or diagnosed with the pre-diabetes, 200 people. See that research. But we want to make sure we're not going to let them getting into that full-blown that type 2 diabetes. That's our whole research is about. See? To prevent that one. See, individuals that develop then now to receive diabetes. So in attempt to stop the progression from pre-diabetes to full-blown. Okay, we can do that one. So then they randomly assign the pre-diabetes patient to receive treatment. They will be assigned to two types of treatments called the normal called the control group, or the same treatment plus the service of a diabetes educator. See, this is a treatment. Then they will be assigned with some kind of a diabetes educator plus that whatever that you have with that normal treatment coming from this control. This is the control group. This is the treatment group. This educator meets with patient on an individual basis and develops a proper diet and exercise plan, both of which are important to prevent in type 2 diabetes. See, that's why it's important. Okay. For this hypothetical study, the dependent variable, which is Y, is diagnosis of type 2 diabetes. See, that's the name of the variable, which is obtained 3 months after random assignment to this intervention group. We will refer to this variable as, if you want, as a diagnosis or health. It has only two options. See, that's the part that I want to emphasize when it comes to our data analytics or statistical part. That's the research part. A value of 0 indicating a diagnosis of type 2 diabetes. If it is 0, 0, 1 doesn't matter which one you want to, that means if you want to say poor health, that's 0. Poor health means they've been diagnosed as having this one. A value of 1 indicating diagnosis of type 2 diabetes. In good health, no such, I'm sorry. A value of 1 indicating no such diagnosis of type 2 diabetes. Good health, poor health. See, two options for Y. Only just two options. It is not the case when we have in a regular regression, we have to have all the time the continuous variable. This time we're going to have a categorical variable with two groups, two classes, two strata. See, two layers. See, these are layers. See, these two are the layers, options. See, this is the variable. This is the variable. We had that kind of a broader discussion in multivariate, even in the repeated measures. Okay. So we have a two option. Because of that, we have to tackle that one in that way. See, on the other hand, our X variables, what are our X variables? Predictors means X variables. The Y variable would be this one. See, this is Y. The predictors means X. Okay. Predictors means X. Those are X variables. See? X variables. See? That's X. Okay. So we can use two variables. Treatment as normal group. See, sorry, the treatment is that's the treatment. Sorry, treatment with two options. See, the treatment as normal group, because the control group, diabetes educator group or treatment group, or another variable you can get involved with this one, a measure of motivation collected from the patient shortly after the diagnosis of indicating the degree to which they are willing to change the lifestyle to improve their health. See, they are willing to change their lifestyle, or they like to change their diet, plus that do they like to go to gym, exercise, or buy their gym and make a gym home or do exercise. And in that way, they can easily prevent being they're gonna have that diabetes too, which gonna affect to that their health issues in large scale. See? So see? They have a two options. See? This look like a categorical again. See, this is categorical. See, they have a two options, two layers, two strata. See, categorical. This looks like a, you can, even this one here, measure of motivation. You can measure of motivation rather than they simply asking them yes or no whether you would like to change your lifestyle. You can just measure that one under certain some numbers been assigned based on that one. Maybe categorical or continuous, doesn't matter for this one. Okay, but anyhow, this is mainly this see, categorical. See, in such a situation, that's kind of a, like a, that's something that you're gonna see in that mainly that I will emphasize this part. This is the part that I will see. And the Y has two options. We don't take into account whether these variables, X variables, are whether categorical or numerical. Okay, so mainly we focus on this one. This is the kind of a like a thing. So when we do that like that, then we can see that is there any association or relationship between the Y variable and the X variables. X variables, okay, and then we can just by keeping one constant, you can think about one variable at a time. Okay, so for this whole discussion, so why then, as I said earlier, sometimes this kind of a situation they tackle like this way. See, look at something like this. You have seen this one. See, see, see. Sometimes see. So each strata, see, outcome present, outcome absent. See, risk factor. See, exposed, unexposed. See, is not in this one, but related to that one. This one you can say that that person in control group or in the treatment group like that. See, in the same way that we can, if you are trying to relate this one to the same example that we have, but what I'm trying to say that it can be that represented by a contingency table like this. This is called the contingency table. With the aid of that one, you can build up some pieces called the risk ratio and odds ratio, something you are very familiar with as of now. You can remember the risk ratio, see, A divided by the total of that one. This one C divided by total. If you take the ratio between, this is a risk. See, having been this one, see? This one, but I'm just showing you that one, but we're gonna do detail that, then you can have a look at it and then get a build up good knowledge on that one. Okay, so so that's a one scenario in which that we are planning to use the logistic regression. Why logistic regression? Because the Y variable is categorical. Okay, Y variable is categorical. When the Y variable is categorical, we are planning to use that one. Okay. Look at another scenario. In another scenario, okay, let's look at another scenario in which that's why we are trying to use this logistic regression. Okay. See, a researcher estimated the following model which predicts the high versus low writing scores on a standardized test. I write. His name is I write using students' gender we name as like a female, and scoring on a standardized test scores in reading, math, and sciences. See? Look at in a situation like this, they were using something like this. See? Look at. So the model would be something like that. See? So in a situation like this, when they have, see, regular. Standardized high right and this one. So what I'm trying to say that when you model this one with the aid of the regular regression, see, with the regular regression, this is a regular regression. This not a simple linear regression. This is a multiple linear regression. Multiple means you have a several x variable indicating how these test scores gonna affect to the this high right. Let see high right and score on a standardized following model which predict means like this one y variable has like a two option, high and low. The variable has been named as high right, and the other variables gonna how they're gonna affect to this one. See? Female categorical, this one also categorical high right, and the math score and the reading math science class level. So if you develop that this regression line, what's going to happen? The researcher would like to know whether this model with the four predictor fits significantly better than a model with just female and read as predictors. Let's say that this is the model. This is not the right model, okay? But let's say if this is the model, now the researcher would like to see. So I'm sorry. The researcher would like to know whether this model with four predictor variables fits significantly better than a model with just female and read as predictors. See, they're gonna drop some variables. See, they get the female means the gender, and the read is one of the subjects, math and science. They're gonna drop. If they drop, how can researcher accomplish this one? See, this model fits significantly better than a model with that one. Different models you can suggest. There are three common types. See, common test or types that can be used to test this type of questions. What are those? Those are same thing we're gonna see. The likelihood ratios test, the wall test, the Lagrange multiplier test, or sometimes called the score test. So these when you run that logistic regression event, they're gonna produce the result for all these tests. The likelihood ratio test, the wall test, the Lagrange multiplier test, sometimes called the score test. These tests are sometimes described as tests for a difference among the nested model because one of the model can be said to be nested within the other. See, difference about the nested model. See, they were nested. Actually, these are heavily utilizing the nested design. And the null hypothesis for all three tests is that the smaller model, since the similar model is that true model is you're gonna get the beta 1, beta 2, beta 3, and beta 4. See? Larger test statistics indicate that the null hypothesis false. You can do the overall test, or you can do the partial test. See? In such a situation. See? You can do the overall test. You can check beta 1, beta 2, beta 3, beta 4. See? All gonna be tested at the same time. That's called the global test. You have done this kind of stuff. I'm just trying to refresh your memory. You see? This test, or you can do the partial test. The way that they have decided over here, when you drop that one, you don't have that two variables being taken out, predictor variables being taken out. See? Female and read only. There are two variables keep, these two are gone. Then you're going to come up with something called the reduced model. That's the reduced model. In reduced model, you have a y beta naught, beta 1 female plus beta 2 read only. Beta 3 and beta 4 are gone because beta 3 equals to beta 4 equals to 0 will be tested in a similar fashion like this. That's another test. It's called the partial test. Or you can think about that individual test. There are three types of tests we're going to get done on this kind of model. Individually, you can check these ones. Are this variable is contributing significantly to the variation in y variable, the variation of the y variable, or that can be significantly described the variation of this variable. That's that one you're going to use one kind of a test, or part of it, beta 1 and beta 2 set to 0, or whole thing like this set to 0. See, global test, if you test to the partially to beta naught or beta 1 or beta 2, something, whatever that 2 or any portion of these variables to 0, that's called the partial test or individual test. Right there. But in a regression, in a logistic regression, we cannot tackle this one like the way that I have written over here. That's what I'm trying to say over here. We cannot do like this. Okay. So, but it is very similar to that one, but we cannot tackle that one. Okay. If that's the case, how could we gonna tackle this one? Okay. Let's look at how we gonna tackle this one. Okay. This is the reason. Okay. Why the least square regression cannot be used. Least square regression means why least square regression cannot be used in a situation like this. Okay, or the first example like this, least squares. Okay, let's get this example, or the example that I talk about in the very beginning, that to prevent that the people getting to the people with the pre-diabetes getting into like a full blown that diabetes 2, and this example. Okay, this one. In that example, okay. Let's see. That's the first example that I was talking about. That I think I mentioned. Yeah, anyhow, okay, that's the other, this the example related to this one. Okay, cannot remember earlier I was showing this one. Okay. Especially this part here. Okay. This is the part that I'm interested in. Y variable has 2 options. The second example is the part that I'm interested in. Y variable. If that's the case, why that least square regression cannot be utilized? Why you call the least square regression means this one. Why we call the least square regression for this one? These all the parameters, you know, these are called the regression coefficients. Regression coefficients should be estimated with the aid of the least square estimation procedure or maximum likelihood estimation procedure. That's why we're going to call that procedure cannot be utilized. The reason is the coefficient, see, standard errors of the coefficient. Standard errors means nothing but the variance, nothing but the variance or the standard deviation of the coefficient. See? Standard errors of the coefficient, estimate of the coefficients are biased, but the coefficients are unbiased. Okay, when you estimate the coefficients, like the way that we have over here, instead of this one, you're not going to write like this way. When you write that this is the population model, you're not going to write the that your model like this. When you have that data, you write with the what, with the b naught plus b1 x1 b2 x2 b3 x3 b4 x4 plus error like that. Those are b naught is nothing but an estimate for beta naught. B1 is estimate for beta 1 like that. Okay, that's why we're going to tell that we cannot use that one, because the coefficients standard errors are what happened, they are unbiased. Sorry, they are biased, but the coefficient are unbiased. And the predicted probabilities, I'm not interested in the value now. I'm going to go ahead and looking into the probability constrained to the 0 and 1 interval only. You cannot think about anything beyond that one. They were constrained to that one. It's not good. The least square regression model typically fits best near the center of the thing, data. See? Thus, it will likely to do a poor job of predicting near the upper and lower values. See, upper value is 1 and the lower value, it's not going to do a proper job because the only two values you can take into account when it comes to the that logistic regression. That's why we jump into the logistic regression. Okay, so I'm gonna these are the reasons why regular regression cannot be utilized. So this is what I'm trying to say. Okay, I can get this discussion built up with one regressive variable or several, doesn't matter. But I'm trying to say that let's say that you have a this beta naught plus beta 1 x1 beta 2 x2 plus, okay, my convenience, I'm going to stick to this discussion to just 2, doesn't matter, 2 or 1, doesn't matter. Okay, if I tell this one, this is what multiple but still linear regression. Okay, regression. Why this multiple? Because of the x1 and x2, both many. If you want, you can add more. Why linear? Beta naught, beta 1 and beta 2 are in linear form, That's the reason. Okay, that's why we call the linear, not because of x, not because of the x, because of the betas. Okay, that one. Okay, multiple regression. See, this is a population version. See, population. The sample version, if you're gonna write, you write y. Okay, I'm gonna say b naught, b1, x1, b2, x2 plus e. Okay, that means b naught is nothing but estimate of this guy. See, estimate. b1 is estimate of this guy. b2 is estimate of beta 2. See, once they were estimated, how come, let's say that let's focus on one of them, beta 1. Okay, I'm going to focus on this guy, beta 1 hat. How come this is just a one value? But that's not the case. If you keep repeatedly doing this one, it will create a whole bunch of value for this one. You know that the broader discussion we had all the time. Okay, in that starting from NR 600 all the way to here, we had that broader discussion. See, you have a whole bunch of values for that one through the simulations. See, so that will constitute some kind of a randomness for this one. Once you have a randomness, those random variable can be put into histogram. When you put into histogram, that will have like a center and a what? The variability. See, for this one, you can see, you can have many of them. See, so you have a B1, see, 1, B1, 2, and then B1, let's say 1000. See, 1000. They are different. Then they constitute what? Random variable. That one you can put into this one and draw a histogram. You can did that one. See, when you do that one, it has a center. Center is nothing but B1, but it's not a regular B1. It's the B1 for the observed value, observed B1. And this is the this one. This is the standard, standard deviation of B1, which is called the standard error of B1. They say this is biased. They say this is biased. They say this is unbiased. This is unbiased. This is biased. That means that if you take the expected value on this one, it would not produce the same value. Like again, the parameter to be estimated like that. I don't want to go to there, but here the same thing. This is unbiased. This is biased. Because of that reason, see, they cannot get that proper the answers at the end of the day. When especially when y variable have two options. We are here. Y variable have two options. Okay. Remember, we have a y variable has two options. This is what we are trying to tackle. Okay, this y has two options. See? That's why, see, y has a two options. See, y has a two options. Sometimes y equals 0, one situation, y equals 1. That's it. See? Two options. Sometimes we have a more than two options. We're going to come to that one later on. So what I'm trying to say, why we are not using this regular regression, least square regression is the case that we are talking about. In order to talk about that one, we will talk about its estimate. This is related to only one of the parameter, but you can apply that one to all the parameters in a similar fashion. They say their estimate center of this graph is unbiased, but their spread is biased. Because of that reason, it's not a good model when we have a y variable has two or more than two options, not the continuous variable, when we have a categorical variable. The other reason, see, all the predicted probabilities are constrained to 0 and 1 only. If you get the probability, we're not going to keep this y and 0 like this. That's not our whole idea. From this one, okay, so then we have y, see, y equals, I'm going to say, sorry, beta naught plus, I'm going to summarize this one like this way. I goes from 1 to 2 beta I xi, it's easy, plus error. Okay, but I'm trying to say that this one has then have a like a, let's say 1, here y equals 1, here y equals 0. You cannot keep like that. That doesn't make any sense. We're gonna assign probability for this one. Probability of y equals 1. Probability of y equals 0. See, it's based on two options. You have a two options. See, you have a two options. See, for each trial, each patient. See, each patient you have a two option. Whether they were diabetes patient, I'm gonna say success based on how you're gonna look at it. Success may be being healthy or being diseased. Okay, doesn't matter. Let's say that being see diabetes. That example or any example, see diabetes or deceased. Deceased and denoted by D. This one failure. That option is failure. Failure means see no diabetes or non-diabetic. Healthy. We can put H or we can say D bar. Same thing, each trial. Then the probability of that, this one you can add the probability of C, D. It's nothing but probability. Let's say that y equals the way that they have taken either way, that when 0 we can say healthy, 0 we can say diseased, 1 we can say healthy. See? So if you want, you can say 0 for this one. Okay. This one I'm gonna say P. This one probability D bar, which is probability y equals 1. I'm gonna say Q. If you add these two, P plus Q equals 1. Probability. Those probabilities always doesn't matter P or Q. See, P comma Q, they will be restricted to what? 0 and 1. It's not good. And on the other hand, our regression model typically fits very well for the center of the data. And what's going to happen to that? They were at the corners. They don't do a good job, very poor job. That's why we move on to, because of these three reasons, have prompted the researchers to move on to a different kind of a model. How are we going to start that model with? Where is this coming from? Where's the beginning? Let's say that, okay, the same thing, okay? This is the same thing. Each trial means each patient, probability y equals 1, success or failure doesn't matter, okay? Either way, okay? Earlier I put the 0 for that one based on that one, but for in order to build up this one, doesn't matter, either way is fine, okay? So each trial, since this is starting from a new setup, I'm gonna say that for my convenience, y equals 1, y equals 0. We have a two options. So see, T and Q, this is a success, this is a failure. They are, see, Q equals 1 minus 1. Probability of y equals 1. See, I'm gonna say alpha plus beta 1. Okay, I'm gonna write this down. Okay, it's easy. The same for this one. Okay. Then I can say probability of success. I put 0. I'm gonna put 0. That's okay. Means beta naught plus beta 1 x if you have one variable. Okay. If you have one variable. See. If you have a two variable, I can say beta 2 is 2. See. Probability has been set up to that one. Not the y, not y. Probability. But what happened was it didn't work either. Then what they did was instead of that one, this is the probability. This is the probability of success. Okay, I'm gonna say success. They're not interested in that one. They are now interested in something called the odds of success. I'm gonna write O y equals 0. See? Odds when y equals 0 is nothing but probability of success, see, over probability of failure, which is P over Q. See? P over Q. P over Q equals to beta naught plus beta 1 x1 plus beta 2 x2. So this one simple capital doesn't matter. When they were not interested in that one too, what we did was we take the word odds. See, then we're gonna take the log on that one. See, I'm gonna take the log. I'm gonna call that one log odds. See, log odds of success. Log odds. It's called logit. See, that's what we call the logit. Log odds. See, so that means see logit of y equals 0. See, take that one still b naught plus b1 x1 b2 x2 to remedy that. See? Then what happens? See? So this is the one. See? See? Logit of y equals 0, or equivalently you can write logit of p with the for the success that one b naught plus summation I goes from 1 to 2 bi xi. See? Logit. I got the probability, I got the odds, I got the their logs. Okay? That would call the logit of P or logit y equals 0. Okay? That's the equation. This is the logistic equation, logistic regression equation, logistic regression equation. You cannot set to y. You have to set to what? Logit of probability of success. See? Logit of P of logit y equals C. See? Y equals C. This one, no, it's the same thing. We can write the logit of probability y equals 0. Okay, that's the same thing. That's the same thing. Now what are you going to do? Well, what's the probability there? What would be the probability? This is the model. This is the model. This is the logistic regression model to remedy the three of that drawbacks we have witnessed on that least square regression and the regular regression. Because of that, we remedied this one and doing some kind of adjustment to that y, because of we have two options on that side, two or many options, doesn't matter. So, and how would you gonna get the p then? How do you get the p? So we know that, see, probability, if you want the probability of success in terms of what be the logistic regression parameters, see, these are the logistic regression parameters now, see, b0, b1, b2, those are the logistic parameters. So now that we have, see, logit of p equals, which is log over p over q, which is beta naught plus summation I equals 1 to 2 beta I xi. Then I'm going to take what? We're going to take the exponential on both sides, log, okay? I'm going to, that one means that this is natural log, okay? I have taken the natural log on this one only. See. Okay, I'm going to set one step over here. Project. This one logic means ln, okay? Odds of y equals 0, which is same as ln t over q, okay? ln t over q. ln t over q. This one. So ln odds of, I'm going to take the log on odds y equals 0, and that is same as ln t over q. ln t over q. This is also, okay, I'm going to write this one, ln t over q equals to b naught plus, okay, if you want you can write like this for your convenience, okay, b2 x2. This is what we call the logit of p. It's very clear. This is the model. Because since we know that one, we can say that p over q equals e to the power of c b naught plus b1 x1 plus b2 x2. See? Then p 1 minus p, q means 1 minus p, e b naught b1 x1 b2 x2. Then we're gonna get the c 1 minus p term cross multiplication, b naught plus b1 x1 plus b2 x2. And by rearranging this one, we can get the p is nothing but, see, e to the power of, see, one over, I'm going to write it this way, 1 over 1 plus e to the power of negative b naught plus b1 x1 plus b2 x2. See? That's the probability. This is the probability of success. See? Have been written in terms of the given regression parameters b2 x2. Okay, this one. This one 1. Okay, this is 1. 1 over b naught plus that one. See, the probability of success. That's the model. It's the logistic model. You don't have y anymore. Y gone. Y will be replaced by the probability of y equals 0 and y equals 1 in the terms of those. And their ratio has been raised to been taken with the natural logs. That's called logit. That's the equation. It's the probability. That's the probability. Probability being given in terms of that one. See? So that's the That's the graph we're gonna draw over here. Okay. I'm gonna narrow down this one to, okay, for the graph. I'm gonna show you the graph for only one. For my convenience, I'm gonna use only one x only, and the probability p is nothing but probability y equals 0. Okay. The graph shape would be something like this is not for if I write this one, p equals 1 over 1 plus e to the minus b naught plus b1 x only. Okay, I'm going to use only one for my convenience rather than drawing this one in 2-3 dimensions. See, like that. That's the probability graph. See, then if you interpret the coefficients, see, b naught, let's say b naught and b1 for this one interpretation. What is that one? The change in logit, see, of, see, for see, change in that one. Sorry, the change of logit in logit of y variable, see, y variable with no x value, no x value, okay, no x value. That means no x value. That means x equals 0. Then x equals 0. Then being 1 is there. That's a change in logit. Okay, change in logit. Can you remember the equation has a logit? So equation has a logit. This is the intercept part. Because of the intercept part is calculated. What's going to happen to the when y value is logit? See, logit of y. See, so what's going to happen to y variable? Not the y variable, logit of y variable when x set to 0, b1, see increment or decrement in, okay, in the logit of y variable, see, y variable for any x value. It depends on that, but the scenario they were talking about over there, based on that one, we can figure out that whether it's going to be yes or no. See, so for the given x variable, okay, so change, I'm sorry, change in any x variable, change in sorry x, change in x, we can put like that, change in x, okay, change in x, it may be categorical low, either categorical low, the comparative doesn't matter, see, doesn't matter. It's a kind of, you have seen this stuff earlier, see. So what we are trying to do over here, there are types. What are the types that we're going to talk about over here? Types. First one we're going to talk about binomial. So binomial and simple. Simple model. Binomial simple model. That means what? You have, see, y. Okay. Y has what? Y has only two options. See, y has two options. y equals 0, y equals 1, like that. Two options. This one is binomial, dichotomous. Then one x variable, one x bar, only one for one. That's why simple. It's a simple. So simple. Second one, binomial, but multiple model. I'm talking about logistic regression model, okay? So logistic regression. Models. See, multiple model. See, y still have, see, y equals 0, y equals 1, see, binomial. See? And x have many, see, x1, x2, x3, see, many x bars, see, and we're gonna say multiple. And third one is multinomial, but simple. Multinomial means y has a many options now. Let's say being denoted by 1, denoted by 2, 3, 4, the categorical, okay? See? Many options for y. X, 1x, simple. See? 1x, simple. The other one, multinomial and multiple. Fourth model, multinomial and multiple. This one has a several options. 1, 2, 3, 4. Several options. X, x1, x2, x3, several x. You can see all kind of these model. There's other names for that one. Multinomial means, binomial means you have, see, two dichotomous. Binomial but multiple. You can have like that. That's a kind of a like example we went through. See? X1 and x2, y has only two options. Earlier, then later on I reduce that one to 1, reduce to this one, doesn't matter. See? The other one is multinomial. See, for the y you have a different options. See, the education levels, see? Education level or anything that categorical, whatever. And then one next, this has to be categorized, but with the two options or many options. On the other hand, your independent variables x may be just one or many. Okay? So we pretty much tackle all these models here. All these models. Okay. So in addition to that one, I think you notice it's a very important part, this part. Okay. I say that what we are trying to say here. When you have a model, how goodness, then we have to check the goodness of fit of this particular model. Goodness of fit. See? Goodness of fit. See that how well this given data fitting into this given model. So we are using three kind of a criteria. Those criteria that when we go to that, let's pull out that one of these examples. So as I said, this example, this is from that CDC, that briefs data, CDC, see, behavioral risk function, sorry, risk factor surveillance system data coming from the CDC, Center for Disease and Disease Control and Prevention. See, I think that data I have already, that you have already used, you use this data, okay? You have already used this data in your previous class. In that way, I don't think that it's a big deal. And plus that it's already been uploaded under that data folder. Okay, you can have a look at it, that one too. So see, I think you have already have that one in your SAS in somewhere in your one of the folders. Okay, so that data, then we're gonna keep this data, the ages, so that this guideline has been given, same like that the data dictionary has been given along with this data. So these data mainly, see, this data I'm talking about, see, Center for Disease Control and Prevention, you have seen that one, see. It's a code book has been given, they call a code book here, but for the data that we are using in our class for the other assignments, we call that one dictionary, data dictionary. The same thing, see, they were explaining that the details about that one, see, the brief overview. And code, this one, data files, see, SQL, and transport one, this one. I use this transport format and then convert it into SAS later on. And the other data, the data that we are using is like his data, see, coming here, see, California Health Interview Survey data, okay. That data or this data doesn't matter, okay. Either one, okay. This data, behavioral risk factor surveillance system data. Those are the two websites. Access to that one. This is our validate this one, okay. So I'm gonna keep gender, diabetes in 1, 3, blah blah, and then use the row variable BMI for cat and call it BMI, the body mass index, need overweight, blah blah, right there. Do the some changes, and then this one guideline. There were some guideline being given in that particular data. Then to change this to that, see, it's categorical like this. See? The sex equals 2, then the sex equals female, male, and the diabetes 2, then diabetes 2, 3, then diabetes 0. They have other options too for this. If you go ahead and look at into that catalog, you can see easily. Okay, there are other options has been given too, but we're going to restrict only to 2 options, and then this has been, see, exercise being changed, and we're going to keep these stuff. Okay, we have already done this one, but so I'm interested in this part. Okay, or this one now. See, any of these. See? Let's say logistics. See, using this data. Okay, I call that one TMP, temporary data, temp to temporary data. I keep in this one. This within the data set. See, BMI for cat. Now they don't call the BMI for cat. It has been changed. Okay, we change that one. No, yeah. See, to normal, overweight, obese, like that. See? We change that one to that. We change that one to this one. We change this to that. We change this to these ones to this one. Okay. And education to this one. The new variables. Now, if you want to run, that's it. Diabetes, see, Diabetes would be your Y variable. See, there are two X variables, exercise, whether you are doing exercise or not, gender. So that both are categorical. Pretty much three of them are categorical. See, diabetes. If you go ahead and looking into diabetes, we're gonna call that one. Where is it? Yeah, see, diabetes 2. That they used to call that one with that variable. When it is 1, diabetes, yes, no, no 0. Here we put like that. Okay. We have coded like that, and then 6, that means see, it's get 1, get 2, or 1 and 2 doesn't matter. Either you use this one or this one, doesn't matter. Keep in head what stand for the 2 and 1 stand for 1. Okay. And yeah, this one, see, they will set this one too, but that's okay. See, we rename again to 6, but it's already over there. That's okay. Don't have to do that one too, just in case. Okay. So then if you run this one, see, this is Y variable, with this a class. See, diabetes reference, we're gonna keep as a 0, gender as a 0, exercise reference, parameter with the reference. See, if you run this one, but I'm trying to show that what are the important one that you have to look into. Look at the analysis of variance, odds ratio. See, 3 test. See, global. See, this test, score and wald, and then this one, model fit. Model fit, that one too. See, these are the tests that I'm trying to talk about with you right now. And then these are the, see, another effect, the parameter estimator. See, intercept is a B node, is a B1, it's a B2. See, you can write that logistic regression model, you can write easily. Then there are odds ratio. See, you get the odds, and then you find the ratios of between the different groups. Okay, let's say that for a given that you have for a X variable, you have a gender, female and male. What are the odds between those two? Called the odds ratio. Okay, you have done that one, those kind of stuff. But I can refresh your memory on that one. Plus that, let's say that instead of that one, if you run something like this with the see, I'm going to add something, aggregate, scale, lack of fit. The aggregate and scale none option request that the deviance statistics be generated, and the lack of fit option request the Hosmer-Lemshaw test. See that? Okay, the same thing. So this time you got this table, see, and this table, and this table. These three, I'm interested in these three. See, these are the 3 tables I'm talking about. Okay. Those are the 3 tables. Those are the main 3 tables. See, so yes, how that you're gonna see that your given data are gonna fit into this model. That's called the goodness of fit, or its counterpart called the lack of fit. Instead of talking about the lack of fit, we're gonna talk about the lack of fit too, but here we mainly that focus on goodness of fit. Okay, so look at the first one, log likelihood. AIC means Akaiki information criterion, and the Bayesian information criteria. Bayesian has another name, Schwartz. On the web, this one you're gonna see Schwartz SC. See, that's the same thing. This BIC. This is BIC, Bayesian information criterion, or Schwartz criterion. Okay, either way. This is Akaiki information criteria. This is a -2 log L. Let's see what do you mean by log L. Okay, you can have a look at it too. Where this coming from, the likelihood, log likelihood. Where this log likelihood come into the picture? What log likelihood? We know that deviance. What is deviance? Pearson. Pearson mainly coming from when we are using the contingency table. You know that broader discussion you had earlier. Okay, This is coming when you are using the contingency table. The same scenario can be tackled with the contingency table. Okay, here let's say I'm going to go back to this one. From this given same example, diabetes. See, this, how could you gonna set up that one if you use the contingency table? For this particular example, diabetes, you have a diabetes is y variable. See, then x variable is let's say you have a diabetes and gender. It's easy. X variable y and x, only x1 variable. See? So go back to this one. See, let's say that you have a contingency table. You're using the contingency table for this particular scenario. See? So I would say here I'm gonna put x variable, say male, female, this one diabetes. Okay, this one we can say this variable y variable, this x variable gender, or x. This one is health, diseased or healthy, see? Like that. No, so you can fill in that, see, these numbers. How many people who are deceased, see? How many male are deceased, how many female are, how many male are healthy, like that, these numbers. See? That's a contingency table. Then you go to these corners and then get the what? Row totals. And here you get the column totals. See? These are column totals. These are row totals. See? These are, see, grand mean here, grand total, grand total, like that. The data of contingency table, you can build up like that. See, but if you have that another variable being added to this one, how could you gonna do that one? Another variable being added. See, here we have added another variable, two x variables. See? We added exercise, yes or no, gender and exercise. See? You can say, see, first one, you can say gender, see, gender, see, and say male, female, then you get the exercise. You can say what? Yes, no, see, yes, no. Based on this one, how many options you have for why? See, diabetes or healthy, see.
Sumith, your battery charge, there it is.
Yeah, thank you. Yeah, I think I can, while I'm writing this one, I can charge too. So then see, that's the way how you can set that up, and then you can look into the numbers and put the numbers, and based on the numbers you can build up that odds ratio and everything. See, like that. You can do that one in contingency table. You can do that. So as I said here, see, but here you're gonna see how that one mainly that this is the one that I mainly focus on, Pearson. Then later on you get that chi-square test and get it done. But here I'm talking about other three tests that are related to our logistic regression model. See, so see, look at our test statistics would be what? See, log likelihood, AIC and BIC, BIC or SC, okay, SC, Schwartz, okay. Is this model better than some other model? Is this model better than some other models? Log likelihood is, see, influenced by the number of model parameters estimated. Okay, look at what happened. When more explanatory means X, okay, X variables are added, better fit in model, but your -2 ln L goes up. See, natural, see, this is what? Likelihood. This is a log likelihood. Okay, I'm gonna talk about that a little bit later. And goes up means larger -2 ln indicates a poor fit again. Because of this reason, it looks like a better fitting, but unnecessary, even the unnecessary X variable, explanatory variables, trying to, even if they were not significantly explaining the variation of Y still in the model. When you fit in into the model, your R squared goes up. Okay? R squared means that like a, can you remember R squared? That proportional PRE, proportional reduction in error. Sum of squared model divided by the sum of squared total. Sum of squared total is nothing but which is coming from the sum of squared error coming from the empty model. You carry so much of the sum of squares error not being explained by this empty model towards you this particular model. Even with the model, not that much of that error being explained. How much error being explained is called R squared, proportional reduction in it. See, it's gonna go up. You feel like it's a good one, but your -2 times log likelihood. This L stand for likelihood. I'm gonna talk about that pretty soon. And that's me. This one indicate poor. Therefore, these people, Akaiki is a Japanese that statistician, top statistician. He came up with this idea, AIC, and the BIC came up with the shorts. Penalize or adjust for the number of explanatory variable in the model. Okay. They were in the model. They were penalized by introducing that one. Okay. So that's the same thing. So therefore, AIC just for the number of explanatory variables in the model. See, Schwartz criterion of AIC. This one, I'm sorry. The AIC means Akaiki -2 ln L plus 2p. P is nothing but number of parameters. K plus 1, where K is the number of regressors. How many X variable in the model is called the regressors, okay? X. But when it comes to the parameters, you have another one, B naught, okay? So B naught, that's why we're gonna add another one to make it number of parameters. B naught, sorry, beta naught, all the way to how many variables you have, beta naught, beta 1, beta 2. In that case, 3 variables to be estimated, 3 parameters to be estimated. But how many X variables you have? X1 and X2, 2. 1 less than the number of parameters exist in that particular model. Then the BIC, see, Bayesian is another framework. Under that framework is a very powerful framework, not like a classical. Classical has so many drawbacks, even though that we work on right now. Okay, Bayesian is based on the prior knowledge, prior information, based on prior information, you're gonna build up something. It's very powerful. So this one -2 ln plus ln n number of observation times p number of parameters. This AIC or BIC you can utilize. Okay. So those values, see. So in this, sorry, back to this one. Intercept and covariate. This is only for the intercept. This is for the intercept only. This is for the intercept only. Either this one or this one or this one, or they can go by this way too, by itself. Only log likelihood or the Schwartz criterion, Akaiki information criterion. So with the including B naught plus whatever the covariates you have. Covariate means X variables, another name, covariates, explanatory variables, independent variables, X variables. That's the same thing. Okay. You can get this part. And the other one, look at the other test. What that test means. The global chi-square test, another test. Is this model better than no model or intercept model? See, this one is this model better than some other model? Some other model. Okay. This one we particularly mention This model is better than the intercept model. Intercept model means like when you have a k-many that variables, all these should be set to 0, and then at least one of the coefficients should not equal to 0. Then this come to see your intercept model is nothing but this one. I think your current model is like this. Okay, with the logic on this side. Okay, I'm writing like this way for my convenience in order to generalize for any kind of a regression. Other than that, for the regression, you don't have a y. The logistic regression, you don't have y, but remember that part as well. Okay, but mainly I'm focusing on this part. See, this will be compared and contrasted with this one. This is my model. Excuse me. This is a full model. This is a reduced model. This is a current model. This is an intercept model. This is a saturated model, unsaturated model, like that. See, can you remember? So if that's the case, your chi-squared should be what? Minus 2 ln for the intercept model minus 2 ln for the current model. That chi-squared should be distributed according to chi-squared. Sometimes people call the chi-squared chi-squared. Okay, number of parameters in the intercept in the model. This one number of parameters in the current model. So that means by looking at this printout, you can remember. See, this value minus this value minus this value, minus 2 ln log 4, including variates. See, this one including that one. This one for the intercept model only. So you can take that subtract and you can get the absolute value. So mainly they prefer to use this one first. From this one 31 920, see, 929 92 11, this one 36 17, 31 31. So you're going to subtract this one from this one, or this one from this one. But the way that we have given, I'm going to subtract from this one from this one. Okay. And that will be compared and contrasted with the chi-square that this with the degrees of freedom. Degrees of freedom. See, that one. For that one, you can use that one. See, see model. See, global null hypothesis. We should go back to the global. I'm sorry. This one. This one. So another way to this one. See, deviance test. So if you, I'm gonna go back to this one. So 31. Okay, see, if you subtract 31 921 31 9 20 11.28 minus 31 36 17.46 5594. That 5594.22 you see here. See, again, this difference you see here, this difference you see here. That's what I want to mention. I'm working on this one, and these three are the tables that we're going to utilize in order to check the goodness of fit of this logistic regression and see whether they're going to well fit into the given data. So in that situation, this minus this one, it is same as you are using the global test. This is global test. I'm on the global test. See, this is global test. Can you remember the other page? We were checking and see, this is called the global chi-square. Global chi-square can be found from here, with the likelihood, here, see, likelihood as a likelihood ratio. I'm going to come to likelihood. Likelihood is a planar role. See, or likelihood as a ratio, or likelihood as a like a difference. Difference in likelihood, log 2 difference in likelihood, same as the likelihood ratio. You know that the log, those are coming from the log rules. The ratio can be expanded as a like a what? As a difference between two logs. That's the same thing. That's the same thing. See, it's the same thing. So that's why either this difference is same as this one. That's what I'm trying to say. And this one, how come it's gonna differ from this one? And this one, we can have a look at it. And this one, AIC, you saw already, AIC and BIC. See, this minus that 31, 96, 17. Okay, so for the other test, you saw that one. Sorry, the other case. When you go up, larger values will be that taken into account, whichever has the larger value. See, so that's another one. Okay, so we haven't done the conclusion, but let's come to the other one too, the deviance chi-square. Is there a better model than this one? The other way around. This one, is this model better than intercept model? Is this model better than some other model? I'm talking about with respect to my current model. I'm trying to keep it, my model, better than some other models. Or my model, whatever the current model, is better than the intercept model. What do you mean by intercept model? All these coefficients are set to 0, no regressive variable, just the intercept only, called the intercept model. My one is better than this one or not. Compare and contrast. And I'm going to check and see, is there a better model than my one? See, my one being compared with others, then others being compared with my one. Now I'm going to compare others with my one. Is there a better model than this one? Few parameter estimated to obtain more probability. See, unsaturated model. See, example. Let's see. There a better model than this one. See, why? Because this model is unsaturated. What that means? What that means here, look at here, beta node, beta 1, beta 2. Okay, let's say this example, this one. I can build up some profiles. Profiles mean 2 to the power of t minus 1. Number of, based on t. T is 3, 1, 2, 3, number of parameters to be estimated, or number of regresses, 2 to the k. Either see, number of regresses, so number of parameters to be estimated. See, I'm going to go 2 to the 4. See, 4. But we have only 3 parameters. We have 4 profiles, 3 parameters. That's why it's unsaturated. That's why it's unsaturated. See, then I have to add another variable. See, that when you add that one, that addition would be significant in explaining that y variable. Okay, here you know when you're going to write the regression, as I said earlier, you don't write the y, you write the logic, but that's okay. See, so we are testing, then it say by my now we have how many variables? See, 1, 2, 3, 4. What do you mean by this? See, this one profiles. See. What do you mean by these profiles? Profile means, see, let's say that for particular this example, okay, I'm gonna, if I stick to this example, how many profile means I'm interested in gender, and then what, whether they were doing exercises. If you do the this one, how could you gonna build up the profiles? And remember, for this particular one, profiles, how could you gonna build up profiles for that particular? Let's stick to that particular one, profiles. So then say that simply I'm gonna say that diabetes, I'm gonna write this, okay? For this example, I'm going to write this on diabetes. Okay, equals beta naught plus beta 1 gender plus beta 2 exercise. Okay, that's my model. Diabetes. I can say this one y, but when you write with that regression, that you don't put like this. Okay, for my convenience, I'm going to say yes or no. Yes, diabetes, yes, 1, no, 0, and beta naught plus beta 1, x1 plus beta 2, x2. So x is see 2, 2, x1 gender. I'm going to denote by x1 gender. I'm going to say male, female. This one male. Male is 0, no? Female is 1. And exercise, yes, no, yes, 1, no, 0. Like that. So I can build up what? I can build up the profiles. See that there. So I'm going to get the profile. Profile has a name A, second one B. I would say C, I would say D. This is a gender. Gender, see, I can say male 0, female 1. Okay. Okay, then I'm going to go to exercise. Exercise male. No. Male, no exercise. Female. I'm sorry, I go to male again. Okay, I go to male. Male, keep that one. Male and yes, 1. Then go to female. Female is 1. No. Female. Same thing that we put into the contingency table. 0. Sorry, 1. Still 1. Yes. Then there are probabilities. Then you know there are probabilities of the disease. See? Probability of disease. See? You know probability of y equals, see? Should be y equals 1. Same as probability of being deceased. It's nothing but, can you remember, 1 over 1 plus e to the minus that formula, e to the minus beta naught plus beta summation. Okay. This one. I can write like this 1 over 1 plus e to the minus what? 0, 0. If you go ahead and put into the formula, okay, I'm going to write here probability y equals 1 is nothing but probability of disease 1 over 1 plus e to the minus b naught, it doesn't matter, b naught or beta naught for my convenience. I'm going to put any of these, okay, beta naught plus beta 1 x1 plus beta 2 x2. See, that's my formula. So when deceased, what is the probability of certain person being deceased given in terms of the logistic parameters? See, that's how we do. But in the contingency table, we don't have this kind of a situation. You can easily find the probability of deceased people when the number of that all of that contingent table being filled in. See, and this one for 2 of them. Want to do that one? See, when these are filled in, you can say probability of deceased people. See, PD, one shot. You get this number divided by the grand total. That's a different story. That's kind of a compared and contrasted at the end of that. But this one is a more advanced approach in order to tackle when you have that 2 options for that one, plus that all that parameters which are random being involved. Okay, the randomness is taken into account. You cannot go in simply like in this route. This route. But I'm not going to talk about that one in this class. It's already thoroughly done in previous class. But this one, when say beta node, see here, x1, x1 means gender. See, gender, x1, x1, this one is x2, x1 equals 0. When 0, male means 0. No exercise means 0. Then if you're going to plug in 0, 0, you are left over with only this guy. That one. So this one, 1 over 1 plus what? Male 0. Male means like that gender 0. Then you are up with a beta node minus beta node plus exercise yes, beta 2. You could plug in 2. Okay. Then here 1 over 1 plus e to the minus beta node plus beta 1. Beta 1, this one, 1 over 1 plus e to the minus beta node plus beta 1 plus beta 2. All come for that one. Okay, I'm talking about this. Okay. See, if that's the case, so odds of being disease, you can talk about the odds too. Odds is nothing but e to the beta node. Odds. And the other one e to the beta node plus beta 2. This odds would give odds of being disease. Odds of being disease means the probability of being disease being compared with the probability of non-disease. That means healthy. Okay, you know that one. So this one beta naught and beta 1. Then this one beta naught plus beta 1 plus beta 2. See? Those are odds. Those are profiles. But we have 4 profiles. See? We have that discussion. See? We have that 4 profiles. 4 profiles. You saw all the 4 profiles. A, B, C, D. But we have a 3 regressive variables. I'm sorry. 3 parameters to tackle that one. We cannot, see, we are lacking something. See, we are lack one variable. We are lacking one parameter. Mainly, that parameter is nothing but the interaction. I added the interaction, thinking that interaction between that exercise and the gender. See, it's a saturated model. Now it's being saturated. It's unsaturated. See, it's unsaturated. How do you check? By looking at the profiles. Now I'm gonna, once you put that one very moment, you have to check and see whether it's significantly contributing. How do you do that one? You do the single testing. See, rejecting H0 allow us to conclude that the saturated model fits that data better than the current model. See, saturated model. If you reject this one, that means you're gonna accept and say beta 3 is gonna stay there. How do you check? You can use this one. See, reduced model, unsaturated model, or current model. Reduced model, because with respect to this one, the current model is the reduced model. See, only see, this is the reduced model, current model, unsaturated model. Any name? Reduced, unsaturated, current model. We're going to subtract minus 2 ln for the full model. This is called full model, saturated model, or suggested model. See? They are chi-squared with the degrees of freedom of the full model minus the degrees of freedom of the reduced model. See? That means the number of regressors in the full model minus the number of regressors in the reduced model, or number of parameters in a reduced model. I'm going to call the P minus for a full model. I'm sorry, full model P minus 1, the Q minus or P minus 1. See, number of parameters in the full model. P, Q mean the number of parameters in the Q reduced model. So for that one, if you take the difference one between these two, see, these two, okay. See, AIC. or this one, 31, 31, see, this one, minus 2 ln. Let's see, 6, 23, okay, so this one, so 4 of them, this one, okay, related to this one, where is that one? I'm gonna see that one. Do I see that? Okay, this one, right, 59, 94, that one, same as that, that's difference of these two. Yeah, yeah, we have to run that one. We have to run this one. I'm sorry. We have to run this one with, okay, run with the this one. Okay, I'm gonna run one more time. Okay. Here with the interaction term. We don't have interaction term. Okay. Okay. Then okay. Then get this one. See, get this one now with the interaction term. See? Okay, sorry, this one, okay. With the interaction terms, look at the deviance, okay? I want you to check something. Deviance 0. Deviance 0. That's why we call that one the deviance test. Okay. So this one reduced to suggested. Okay, I'm gonna go back to that other model. This no, sorry. Okay, this one. Okay, this is 31, 31, this one 31, 920. 5714. And this one, this is for the intercept model, this one, okay, 31, 34. I'm gonna write it down. 31, 34, 96.49. This value. Okay. That's with the interaction terms. Okay. So I'm gonna go ahead and get with that with interaction terms. I'm gonna run this one without interaction terms. Then I go to the minus 2 ln 31, 36, 70, 31, 36, 36, 17.46, 120. See, they say this one, this is what I'm trying to say. This one, this 120 that you see here is nothing but this value. See, this is for what? Without interaction. Okay. And if I run this one again with interaction term, that difference, see, okay, one more time here. Without, see, without interaction. See?
I think you've got the wrong screen now, right?
Is that right?
Your output went away.
Oh, no, I'm showing this one, the formula. No, can you see this one? Can you see the formula?
Yes, I can see it.
Oh yeah, but I'm trying to say that I'm trying to say reduced model means like a without interaction term. Let's calculate this one, okay? And with interaction term, we just calculate this one. Get the difference. That difference should be same as the deviance that you see here. That's what I'm trying to say here. So you run this one here without interaction. Okay, that value 4 minus 2 ln. So for this one, I'm here. Okay, I'm not minus this one. That test different test. This value 31, 36, 17. 31, 36, 17, 31, 36, 17.006. Okay, I'm going to keep that one, this value. Okay, remember this value to deviance value. Okay, deviance value. So this one, I'm going to minus the minus 2 ln L value coming from the interaction with the interaction terms when we run with interaction terms. Okay, then I got, forget about this one. See, 31, 34. I'm going to subtract 31, 34, 31, 34, 96.49. That is 120.57, not here, because the deviation has been taken out. Now I'm going to go back to without interaction term. This one run again. And then show that they are deviance. Under deviance, you see the same thing. 120.57 is same as you subtract this one minus same value with interaction term. That is the deviance. See, then you don't have to calculate. It's already there. That's what I'm trying to say. But if you try with the, because they say that this one, they indicate and say, hey, your unsaturated model is 120.5701 units away from, it has been measured with a certain unit or some, away from the saturated model. Push that one to a saturated model. See, this much is my deviation. How far that is deviated from the saturated model? By this much. See, this much. How did you get that one? According to theory, it says, so this minus 2 ln part or likelihood. See, you can simply say the likelihood for the reduced model minus the likelihood for the full model. If you take that difference of that one, that is same as. But once you saturate, you can very clearly see. Once you saturate, don't go to the deviance. Okay, I'm going to run deviance one again. Sorry, this one, saturated model, I'm going to run again. And go to deviance. Very clearly say, no, you are done. See, this indicate you're done. Don't go any further and then try to do that one, because that your interaction term is significant. See,
So is it also because it's saturated, like we've explained all the error because all of the interaction terms are accounted for?
yeah.
Is that why that's zero?
No, not all. Just one interaction term I added here. One interaction term. See, one. See, that's only one interaction term in my model. See,
But that's all of the possible interaction terms. Oh, you mean like if it was sex and interacting with sex again? But because
oh, no.
that's it, right? There's no more interaction terms that you could possibly put.
Yeah. For this one, there are no.
Right.
Like I'm restricting my two variables to only two. That's why. If you have a more, then you have to go for more. Okay. That's a different story. But I'm based on this one for my convenience to make this one easy. So I went with this one. This interaction term, you check. As you said that if you have a more interaction terms, you have to check them as well. Okay. So all the interaction terms. So I'm sorry. Okay. So here this interaction term, because with this interaction term, that becomes saturated. With this one, answer. Then we have other models in which that we have so many of them. Let's show you another one. More with the more interaction terms. Something like this. Let's see. Okay. See, colon cancer, alpha means the beta node, beta 1, smoking, sex, age. See, how many profiles? See, number of regressive variables. Age should be there. So their profiles is built up like this. See, the smoking, you know, see, this one gender. No, see 00, certain age greater than 55 and less than 55. See, if it is greater than 55, 0, less than 55, 1, those are, see, categorized to age, gender has been categorized, smoking has been categorized. Our response, which is whether this person is diseased or not, been categorized. It is the key part. This is the key part, disease, because that's why we are using logistic regression. These are, otherwise we don't use the logistic regression. But as you said that we have a more variables, means it, deviance test means it, interaction terms. You can check the interaction terms. One by one, we have to check everything. Okay. But in this case, but what I'm trying to say is whatever you do, those three tables, then you saw that when it comes to the global test, see, I talk about three tests over here. I answer, one is called the deviance test, the other one called the global test, the other one called the likelihood ratio, likelihood test, or simply you can say likelihood test. Three tests. You're gonna see what is the question. Is this model better than some other model? My model. I'm being compared with others, not others being compared. I'm trying to see and see whether my model is this my model. The current model is better than some other model. Current model is better than intercept model. Oh, is there any better model than my model, the current model? That's the deviance. Then in order to tackle that one, you have to look into the profiles, and the profiles shows that the four, but you have a 3 parameters, not enough, unsaturated. You make that one saturated, and not only that, you run the test. In order to run the test, you need the test statistic. You use the test statistics. Test statistics is not only enough. You need its only related distribution. It's already there, and not only that, you need their degrees of freedom. Everything very Mr. mentioned here related to that printout. What I was trying to say that whatever you see on these results, but based on, sorry, whether you run this one or this one, whether this one, when you run this one, see, the global test is being tested by taking difference between these two, which is this one again. Now, not only that one, in addition to likelihood ratio test, you have something called the score test and the wall test. Okay. So here, on the other hand, and if you're gonna subtract this minus your new saturated models, this value, that is same as this value. That's what I'm trying to say. So if you want to see that the deviance test, you can easily pick this value can be compared, contrasted with the chi-square, with the degrees of freedom, that degrees of freedom, and say whether your value gonna be that you can reject H0 or not. You don't even have to run that one. That's what I'm trying to say. See, it's already displayed along with the that unsaturated model, and say, hey, in order to make this unsaturated, do some kind of adjustment. We did the adjustment. Once you did the adjustment, the deviance becomes 0. That is same as this value and the previous same value, their difference is, okay. Now it is 0, but the earlier printout you saw that one. Okay. So that's kind of like a that one. So in order to support that the global test, if I come back to the global test one more time, global test means this one. You're gonna see whether my this test, see this my model is better than the intercept model. This can be get it done by setting this is my H naught and this is my reduced model. This is my the current model. Okay, current model is my current model is full model. My other model, suggested model is reduced model. But when it comes to the other one, my current model is reduced, the other model is full. Okay, try to distinguish those two very clearly. In order to get this done, you can use this one, this minus this chi square. So with this degrees of freedom, you don't have to calculate this one. It's already displayed. Where under global test, that's what I want to tell you. Under global test, see, under not this one, sorry. When you run this one, okay, without knowing anything that you are not there on the third test. You see, this is this one. These two differences same as this one. Not only that, now we have another 3 tests to be taken into account. Let's see what these are. And in addition to, okay, I'm going to go through that one real quick and then we continue same discussion on this and keep going. Okay. So what I'm trying to say, something like this. Comes to test. Oh, wow, no, yeah. Test. See if I can show. This one, okay. Second. Okay, look at something like this. From here, okay. See, this is something we refer to as the wall test. See, okay. The wall test means, let's say that this equals that, the regular test. See? This one normally distributed standard error. And if you square this one, this guy square, this value is chi square. See, that's the wall test. The standard error is nothing but t hat times the p hat divided by n, p hat q hat divided. We know that one. Okay. We don't have to worry about that on that, but I'm trying to say that the value will be displayed. Value will be displayed, chi square value, this value. What I'm trying to say, this value will be displayed, not this side, this one. We have calculated this one and they have put that one under H naught. Under H naught, you know this value beta naught, or they equals to in a global test that I showed you earlier. They all are 0. You can put a 0 for that. Okay. I'm talking about for this one. Okay. For related to this one. Okay. Related to this one under H naught, this part becomes 0. That's what the rest gonna be over here with the vectors. They can tackle. Okay. I'm not gonna go to detail, but I'm trying to give a rough idea, thinking one at a time. Okay. Now they were thinking about all of them are zeros. That's okay. The same concept. Okay. One of these gonna be 0 or that all gonna be 0. That's a kind of the same idea, but I'm trying to give the idea only. Okay. So this is the value. It's already, they have already given that value. We don't have to worry about that. Then what is the score test? Score test is you're gonna use this one. Okay. Instead of using p hat, look at the difference. I'm using for the standard error P hat and Q hat. See? Instead of that one, they are using the standard error for this one. See? P naught value, P naught value, see? Under H naught value. Okay, just a rough idea. Okay, rough idea for that one instead of that one. And the likelihood ratio test, they're going to use that one. You're going to find the likelihood under H naught and this one under HA, their ratio. See, under H naught and H1 is the same as I'm talking about this one. That's the same thing. It's the same thing. See, this one. See, this one. Okay, if I pull out the minus, see, this become plus, this minus that. Okay, minus minus plus. See, so 2 times, see, this one, this minus that. So that means when you take the under L, the current model divided by the, see, this one under what? Under HA. This one under HA, this one under H naught. See? Under H naught, you have an intercept model. That's the same thing we were talking about here. Okay? That's the same thing we were talking about here. Okay? That's how these three differ from each other. They're pretty much the same thing, but differ a little bit slightly different from each other for a certain reason. Okay, so one more thing I can show you real quick, and we can show you one more thing to get an idea about the likelihood, what happened to the likelihood, because we talk about the likelihood in large scale. Now you know how the likelihood is going to play a role in our discussion, in this discussion. Okay, 1 second. So all this. Okay. We know how this, okay, this is how we got the logistic regression into the picture. Okay, this part, the last part, that's okay. We did that one. We get the p value. See, in this format, we have the p actually solved in this format. And this one, we talk about this one too. Okay. Here, little bit real quick, just give a rough idea. So let's look at that. Each trial, I'm talking about the y variable, okay? Y variable, how many sample size means how many patients? Let's say in our discussion from the very beginning, 200, each person, whether they're gonna have like a diabetes or not, see, success or failure. If that's the case, that can be modeled with the probability mass function, see, probability y equals y, not only y equals y maybe either 1 or 0, you can set up like this way. See, look at when y equals 0, if you put 0, you get the 1. See, 1, it becomes 1. See? Sorry, p. I'm sorry, p. You become p. See, same answer. Instead of talking separately, like this in the tree diagram, the mathematicians, they put both together to tackle easy. This one more schematic diagram only. It cannot be even cannot be fed into even into the computer like this format, because the machine doesn't take like this way. This is easy. They put this formula inside and say when y equals 0, see, when y equals 0, this become 1 q. See, y equals 0 q. They both been tackled that one. That's what we call the probability mass function. Then likelihood function is nothing but the product of all these values for each and every individual. Every individual carry this much. Whether that person is a disease or not, it's already here. So every individual has this part. those parts should be get as a, like a product. I goes from 1 to n as a product, okay? It's a product. The product becomes summation on the exponent. You know that one. See, the exponent becomes summation. See, okay. See? So then see this one. That's what we call the likelihood function. Then I took the log on that one. When you take the log, the sigma y, this part come to the front, and then log p like this. Then I take the first derivative, the partial derivative with respect to the probability is called the score function. It's the score function. It's the likelihood function. See? That's how the likelihood is. This is the likelihood they're talking about all the time. Okay, but when it comes to, they keep going, but you don't have to worry about that one. But under the likelihood ratio test, see, likelihood under the H naught divided by likelihood under MLB. Okay, and plus, okay, then they say that you want to test this one, test something, okay, or test this one. See, you can get the regular test statistics, this one. See, or you can get the likelihood ratio, means like you're going to get under H naught, you're going to get the likelihood, which I showed you earlier, and under MLE, maximum likelihood estimate. Or you're going to square both sides, then you get the word. See? Then you get the, see, the first derivative 1 square divided by this one, but you don't have to worry, but that's how you get the score function. But when it comes to that regression, logistic regression, we replace that this part. You see, in the likelihood function, this p, I'm gonna replace by this whole bunch. See? But this cannot be solved. This has to be done numerically. That's why we have a 3 test to check that one. See? This one, see? L. My L is nothing but in logistic regression. This is the part I'm talking about. This whole value is my likelihood. And log likelihood is, if you take the log on this one, that part times -2 is the one that displayed over here. See? That L -2 times is the value. We don't, that's why we don't do by hand. With the machine has been fed with this, all the necessary formula, we don't have to worry about anything. You have to interpret the results. That's it. Okay. So I think that we keep going on this one, and then we're gonna add more flavor to this one. We can, and then we can have a look at it. Our homework 4.2. See, sorry, homework 4 that I'm using that other data that we are using in this class, and see, I talking about that 3 models here. See. And the descending means like a when in the ordinal. Ordinal means it has been order 1, 2, 3, 4 like that. See, look at this one. AB1. AB1, I'm going to say AB1 means general health condition, not like only 2 options here. See, 5 options. Poor, fair, good, very good, excellent. And I'm going to make sure I'm going to keep the reference as a 5th one, poor one. With respect to the poor one, what's going to happen? This is my Y variable. So this is multinomial multiple logistic regression model, this one. See? Then it has been given by, explained by the education, sedentary, these are their gender, income, and marital status. See? See? Marital, see? All are, see, most of them, see, income categorical, categorical, categorical. Even education has been categorized. We're going to categorize here, education, see. I'm going to categorize education. Convert a categorical AEH. Everything you can get it easily from that that book, okay? The book, what that book from the dictionary, that data dictionary. Can you remember? If I show you something quickly, how to get that one? Very, okay. This is what I'm talking about. Homework week 1, his dictionary. When you they say that, let's say it is clearly given on number 17, page 17, okay? When you go to page 17, I'm sorry, here, let's say AE, okay, this one, okay? This is you are interested in. Now you need the description. They say go to the data dictionary, now 16 page 16. This is not page 16. You have to add 48 pages. 48 plus 16, 64. See, 64th page. See, you have to add 48 pages, okay? Because it's on the I think after the 48 pages, it's going to be displayed on the 17, because this is going to go all the way to 48 pages until it finish the description. Even though they say simply go to that one, AB1, okay? Sorry, AB or anything, any variable. On the 17, you have that number 5 under that one data dictionary variable listing. Now you are interested in this variable. Okay, so this variable, now they say it's on page 16. It's not on 16. 16 already you passed. You have to add 48 pages to 16. 48, okay? Add, see, add 48 pages. Plus 48 pages. So then 16 plus 48, 64. That's why I statement to here. 64th page. See, maybe not. Okay, like that. Okay, I'm gonna go ahead and then stop over here, and then let's continue same discussion on Wednesday and Thursday, and then we can finish everything. Okay, I'm gonna say you guys have a good night, stay safe and be well. Okay, see you on Wednesday. Thank you.
Thank you. Have a great evening.
Thank you. Take care. Bye bye.